Hello everyone, welcome to Prakriya Educations. I am Mallikarjuna. This is third out of 7 modules of determinants. In this module, we shall be solving some problems on properties of determinants. Look at the first problem. To prove this, let us start the problem from LHS. Now, you can find that in this problem, in the first column, all the elements are equal to 1. In any of these kind of determinants, that is, if in a determinant, if you are finding any one row or any one column equal to 1, then we can apply the operation like this. I can change R2 to R2 minus R1. And I can also change R3 as R3 minus R1. The main aim is to make maximum number of zeros in any of one column or any one row. And using this operation, we now get the changed determinant as the first row you are not changing and hence it remains as it is. The second row is changing as R2 minus R1. Go on subtracting the corresponding elements 1 minus 1, 0, b minus a, and the third element b square minus a square. We are changing the row 3 as again the subtraction between R3 and R1 elements, and hence we get now. You can find that in the first column we have got 2 zeros, which helps us to expand the determinant in a very simpler way. Now again simplifying this given determinant, we get the first column remains same, the second column also remains as it is. In the third column we can now make b square minus a square. We get b minus a into b plus a. And in the third element, c minus a into c plus a. Now, you can find that in R2, you can take out b minus a common, and simultaneously in R3, you can take out c minus a common. And hence, writing the operation, that is, I can now take b minus a common from R2 and c minus a common from R3, and therefore the whole determinant changes to b minus a into c minus a, which are the common out terms. The left determinant will be. We have now made the determinant very simple, and even now you can again simplify. Since you are having ones here, you can again subtract these two elements. That is, I can apply the operation R3 changing to R3 minus R2, and hence again we get the changed determinant as. You can now check that c plus a, which is the element of R3, minus R2 corresponding element is b plus a. Simplifying this, we get c plus a minus b minus a. A gets cancelled and we'll be left with c minus b, and hence the element here will be c minus b. Now you can expand this determinant, but using the property you can see that the lower diagonal elements are all equal to 0, and hence you can now multiply the principal diagonal elements, and which fetches you directly the value of determinant, and hence LHS now will be equal to b minus a into c minus a. Multiply the principal diagonal elements, we get c minus b. You can now check the elements which are given in the proof. We need a minus b and we are having b minus a. We need b minus c, we have c minus b. C minus a is needed, and yes, we have that. From these two elements, you can now take common minus, and hence we get minus common from this element, we get A minus B. This element remains as it is. Again minus common in the third element, we get minus of B minus C. And therefore minus into minus plus, and hence the final answer is A minus B, C minus A, B minus C, which is the required result, and hence we have now proved the result. Look at the next problem. To prove this, we shall again start with the LHS. You can check in the LHS that the elements which are in the row wise are given in a cyclic order. For these pattern or these kind of determinants, we can initially use the operation like this. I can change the first column elements as, I'm changing the first column as, I can add all the three columns, and hence we get C1 plus C2 plus C3. The resultant determinant now will be equal to x plus x, 2x, plus y plus y, 2y, plus 2z. In the similar way, for this element, z plus z, 2z plus y plus y, 2y plus 2x is as it is. For this element, again the same way, we get 2z, 2x, 2y, and these two columns retains as it is. Now you can look that in the first column all the elements are identical, and hence now I can take 2x plus 2y plus 2z common from the first column, and hence we get 2x plus 2y plus 2z into the determinant 1, 1, 1 after taking out common the leftover elements. Check for these elements now. The determinant now is having in the column 1 all the elements are 1. As in the previous problem, you can again operate these rows like you can operate R2 minus R1 and as well R3 minus R1, and hence now I'll apply the operation R2 changes to R2 minus R1, simultaneously another operation, that is R3 changes to R3 minus R1. When you are proving in the determinants or when you are applying the elementary operations in the determinant, then you can use the column operation as well the row operations simultaneously. There is no restrictions as in the matrices chapter. Now continuing this, we get LHS equal to, I can take out 2 common from these terms, and hence we get the first row remains as it is, the second row 0. Now for subtracting these two, y plus z plus 2x minus the corresponding element in R1 is x, and hence if you are solving this, you are now getting the element as y plus z plus 2x minus x is x. Fine. Then y minus y 0. Now for the next operation, 1 minus 1 0, x minus x 0. Again for this element, that is z plus x plus 2y minus corresponding first row element is y. Simplifying this, we get z plus x plus 2y minus y gives us y. Now you can again take out common x plus y plus z from R2 as well x plus y plus z from R3. That is one of the option, or else you can also check that you are having all the lower diagonal elements equal to 0, and hence directly you can even multiply the principal diagonal elements, and hence we get LHS equal to 2 times x plus y plus z into 1 into y plus z plus x into z plus x plus y, and hence we get x plus y plus z the whole square. Multiplying, we get LHS equal to 2 times x plus y plus z the whole cube, which is the required result, and hence it's been proved. Look at the next problem. This is a quite different type of problem. Let us again start with the LHS. In the first step, I shall take out A common from R1, B common from R2 and C common from R3, and hence now we get LHS equal to A from R1, B from R2, C from R3, the common terms. Now the leftover elements will be, if you are now having A square plus 1, A square plus 1, if you are now taking out common from this term, A will be left over, plus from 1, if A is taken out common, you are being left with 1 by A, and hence the first element will be A plus 1 by A, and the second element B, then C. Again B from R2 is being taken out common, and hence A, the same fashion B plus 1 by B, and the third term C. In the third row again we have A, B, C plus 1 by C. Now we shall apply the operation R2 changes to R2 minus R1, simultaneously R3 changes to R3 minus R1. Now the LHS will be equal to, the first row remains same. Now the second row elements, if you are now subtracting these elements, the first element A minus the corresponding element in R1 is A plus 1 by A. Use the brackets to avoid sign mistakes, and hence we get A minus 1 by A, and we'll be left with minus 1 by A. This will be our element of R2. Now subtracting these two elements, B plus 1 by B minus B, we get the answer as 1 by B. Here C minus C leads to 0. Now for this term R3 minus R1, A minus again this term we get minus 1 by A, B minus B 0, and this term C plus 1 by C minus C, which gives us 1 by C. Now in the next step, the LHS will be equal to ABC into, I shall take the LCM, and hence we get A square plus 1 by A minus 1 by A minus 1 by A, the first column elements, B 1 by B 0, C 0 1 by C. Now we shall again take some elements common. Take 1 by A common from C1, 1 by B common from C2, 1 by C common from C3, and hence we will be left with LHS equal to ABC into 1 by ABC, which has been taken common, and the left out determinant will be equal to A square plus 1 minus 1 minus 1. B square, when you are taking out 1 by B common, B will be B square, and hence here 1 0, C square 0 1. Now ABC gets cancelled, and LHS now will be left with A square plus 1 minus 1 minus 1, B square 1 0, C square 0 1. Now we have no other option to much simplify the determinant, and hence now I'll expand this given determinant. You can expand the given determinant with respect to any row or any column. Now I would like to expand this determinant with respect to R1, and hence we get LH is equal to, and therefore we'll be left with A square plus 1 minus into minus plus B square plus C square, and therefore LHS is equal to 1 plus A square plus B square plus C square, which is the given result, and hence proved. That's all for this module. Please don't forget to like, share and subscribe the channel. Thank you.